Okay, good. It's recording now.
Okay, thanks, Dr. Kai-Sun. Good morning and good afternoon, everyone. My name is Ling Zhu. Currently, I'm a senior tech leader with the R&D group, Transmission Operation and Planning with EPRI. My focus area is grid monitoring, analysis, and control using synchronized measurement data. So today, the topic here is my title of my presentation is Inverter-Induced Forced Oscillation Source Location Estimation using Synchrophasors SRP case study. It's a South River project. It's a utility in Arizona state. So this is the teamwork among EPRI, SRP, and also UTK. So just a quick background of the forced oscillation. I think all the audience here are familiar with forced oscillation. So we observe quite a bit major oscillation event in the eastern connection and the western connection. And then the troublemaker could be the synchronous generators and also the battery energy storage system or IBRs. For example, in 2022, that is the energy storage system in Southern California. And the multiple events happen in the Arizona area, but the whole western connection can observe the oscillation because of something wrong with the battery and energy storage system in Arizona. So here is just a quick summary for this is a NERC recommended practice and also mitigation measure for the forced oscillations. So there are 3 phases and also 5 steps. So first step, you need to detect the forced oscillation to be aware of what is happening in your system. And the next step is to determine the oscillation frequency and the magnitude, and also determine whether the oscillation is severe or not. And in phase 3, we need to identify the source location. So step 4 here to determine where is the location, roughly the location of source. And then we need to specify which is the component causing the oscillation. And we need to narrow down to certain unit and also either the active power issue or reactive power issue. That's a recommended practice. And also there now is an industry practice for now. And to that end, this is a multiple-year effort to develop this tool. The tool we called the Forced Oscillation Localization Tool. Originally, the tool handles the traditional forced oscillation, let's say around like a 0.2 hertz or 0.1 hertz to 2 hertz, a few hertz. So right now we expand the frequency range to 2 directions. One to the ultra low frequency oscillation, usually is less than 0.1 hertz. The tool is also able to identify the source location and source type. To the other end, direction, the tool is able to handle the high frequency, usually is the IBR-induced forced oscillations or SSOs. So right now I saw an example is up to 15 hertz. It depends on your PMU reporting rate. To estimate the source location, we have implemented the 3 different methods to estimate the source location. Number 1 is a dissipating potential. It's a modified method based on the dissipating energy flow. The second method here is based on the the oscillation magnitude. And the third method here is based on the oscillation mode angle. The result from the synthetic result of all the 3 methods will be treated as the final result of the tool, and the source location can come up with a confidence index. In addition to the source location estimation, the tool is also able to estimate the source type. So let's say either the active power control loop issue or reactive power control loop issue. So for example, if the source is a synchronous generator, we can identify it is a governor control issue or exciter control issue. Similarly for the IBR, if the IBR is identified the source, the tool is able to tell you whether the active power control loop issue or reactive power control loop issue. Additionally, if the forced oscillation is the interconnection-wide issue of forced oscillation, with limited PMU memory within one utility or ISO, the tool is able to identify whether the source is inside or outside your footprint or territory. So usually this is for the interconnection-wide forced oscillation event. And the tool does not rely on the system topology, and we do not require the full grid PMU coverage. But certainly, more PMU, the estimate result will be more accurate. This work is in collaboration with the University of Tennessee. The diagram here just want to show the input, output, and the configuration of the tool. Basically, the input here is a synthetic and recorded synchrophasor measurement as input. As you can see on the left, the input data, we can use the voltage magnitude and voltage angle and the frequency measurement, and also the PMU locations. So either the GPS coordinate or zip code or the county name if the GPS coordinates are too sensitive to be provided. All of the three here, measurement, the data are the mandatory input. Additionally, we can use their current measurement and also line parameter as optional input. And output here is associated with the function of the tool. So the tool can output the estimated source location with confidence index. And also we can provide the estimated source type and also indicate the source is inside or outside your territory. And also additionally, we can provide some intermediate results, like for example, FFT and NES results. Regarding the configurations or settings, we can allow the user select the method and give them different weighting factors. And also they can specify the data reporting rate and also the data window selection and also frequency range selection. So what kind of the frequency range is of your interest? And a little bit of detail about each method here for the source location estimation. So number one here is a dissipating potential. So as we know, the dissipating energy flow is a very typical way or method to be used in industry practice for source location. So once we have a forced oscillation event happen in the real system, that means that we have an external disturbance or source to continuously perturbate the power grid. And then the oscillation can be propagated to the entire grid. And the propagation of the oscillation will be very similar to the propagation of the waveform. You have a water drop to the lake or water phase. And the idea here is to develop a modified method based on the dissipating energy flow. We call it dissipating potential. The method or idea here is very similar to the DC circuit. As you know, in a DC circuit, the power or current, active power or current flow from the high voltage side to the low voltage side. So here we use let's say we got the PMU measurement, and we know their PMU location because of the GPS coordinate. And then we can build the virtual line among all the PMUs. And based on the virtual lines, and we can use the measurement frequency and the voltage angle to estimate the dissipating energy flow among all the virtual lines. And based on that the dissipating energy flow of all the virtual line, we can estimate the dissipating potential of each PMU locations. And the location with the highest dissipating potential, that's very similar to the high voltage as the DC circuit, that will be deemed as the source. And you can see here, this is one example for the January 11, 2019 EI forced oscillation event. And the Florida area, which is the actual source area, has the highest dissipating potential. And this method is usually assigned with the highest weighting factors. So that means we trust this method more than another two methods. The second method here is very simple. Usually, but not always, the oscillation source location has the highest oscillation magnitude. But as I said, it's not always the case. So this method is usually assigned as the lowest weighting factors. Again, the same event in the EI and in 2019, and the source area has the highest magnitude. In this event, it's roughly 110 millihertz peak to peak. And the third method here is based on the oscillation mode angle. So the idea is very simple. It's based on the it's very similar to the power flow angle. You know, for the power flow in the AC circuit, the power flow is always flowing from the angle leading area to angle lagging area. So based on the measurements, let's say either frequency or voltage magnitude, we can calculate the oscillation mode angle at a different location. For example, the PMU, you can see bottom left, the figure here shows the PMU1, the oscillation mode angle is leading PMU2 by 35 degrees. And you can see here, this is another event. That is the event for the calculated oscillation mode angle for the event in January 11, 2019. And the Florida area has the highest leading mode angle. So that is can be treated as the source location. This method is usually assigned with the intermediate weighting factors. So as I said, the three methods, they can estimate the source location independently, and the synthetic result based on their different weighting factors. The synthetic result of all the three methods will be used as the final result of the tool. In addition to the source location estimation, the tool is also able to estimate the source type, either active power control issue, for example, governor, or reactive power control issue. The method here is very simple and straightforward. If the active power control loop is the source type, usually at the source location, the oscillation magnitude in frequency is larger than the voltage magnitude. And also the oscillation mode angle in frequency is leading the voltage measurement. As you can see, that will be in the red dots here. And on the other hand, if the reactive power is an issue, so typically the oscillation angle in frequency is less than the voltage magnitude. And the oscillation mode angle in frequency is lagging the voltage magnitude. So based on that, we can identify which would be the source type. But in the middle, if they're hard to tell, we can say it's an uncertainty. The confidence index will be really low for the source type estimation. And the third function is to identify whether the source is inside or outside your footprint. So we use the dissipating potential method to identify the source location. So for example, we can manually or label the PMUs inside or outside your footprint. For example, the PMU 119 is outside your footprint. This is the other end of the interface line between your own area, L2, and your adjacent area, area 3. And areas, the bus number 134 and 132, those are the boundary bus. That means the one end of the interface line inside your study region, inside your footprint. And the bus 1088 is inside your territory. So we can perform a source location based on the available PMUs inside your available PMU inside your footprint. For example, it's one utility or ISO. If the identified or estimated source location is 119, that means we can say the source is outside your footprint. And if the source at the estimated source location is on the boundary bus, let's say 134 or 132, we can say this on the boundary. It's hard to tell the source is inside or outside. But if the estimated result is inside bus, let's say 108, the tool can tell that the source is inside the footprint. And also the dissipating energy flow from the interface line can be provided as a reference, but that cannot be used as criteria to say it is inside or outside, to identify the inside or outside. So this is the algorithm we use or implement the tool to identify the source inside or outside the territory. Additionally, as I said earlier, the voltage measurement is the mandatory input data for the tool. And the current parameter can be, and also the line parameter, and also the transformer parameter can be used as the optional input of the tool. So here we, based on the voltage and also the line current, we can perform the linear state emitter to improve the grid observability to provide a more pseudo or estimated PMU measurement. For example, for the interface line, we have the voltage measurement on one end, and also we have the line current from the flow this interface line. And if we know the line parameter, we can perform the linear state emitter to estimate the voltage of the interface line of the other side, for example, the VJ here. And in this way, we can expand the grid observability. Yeah, that's the basic introduction of the offline version of the tool. In addition of the offline version tool, we have the online version of the tool as well. The online version of the tool is implemented as on the OpenPTC as OpenPTC adapter. This is a user-defined action, and also has a separate GUI. And the tool, online version of the tool, is able to interface with your enterprise level software or hardware PTC. So you can see here, the streaming synchrophasor data will be input of the tool, and the tool is able to automatically detect the false oscillations. And after the oscillation is detected, the tool is able to automatically perform the advanced analysis to estimate the source location, source type, and also identify whether the source is inside or outside the footprint. As you can see on the right side, there's a GUI of the tool. This is a tree view to display the detected false oscillation event, historical event. And if you click each of the events, it will show the advanced analysis result, including the dominant oscillation frequency and also source location, inside outside identification, and also source type, and plus the estimated dissipating energy flow as the interface line. And also we can visualize the source location on the GUI. Yeah, and after that, we have performed quite a bit case study with the simulated event data and also the actual event data. So today, I will focus on the actual event data case study. So as you may know, there are multiple events happening in the SRP and multiple false oscillation events. And because the frequency is very close to 0.25 hertz, which is able to interact with the north and south A mode of the Western connection. So once the event happened, so the whole Western connection can observe the oscillations. And the troublemaker is a few energy hybrid power plant with solar PV and also the energy storage system. And you can see for the first event happening on September 20, 2023, the root cause is an error in metering the loss compensation methodology. So they have the algorithm mistakenly divided by 0. So the reference of the active power is a very large value, so back and forth, and trigger these oscillations. And another event on November the 3rd, 2023, when they do their commissioning testing, the PV output is hard-coded to 0, but they forgot to change to the real value after the commissioning. So that's leading to the meter switching logic error and creates the false oscillations. And all of the 3 events, we see there's a source type is active power control loop issue. So yeah, later on we contact the SRP and we perform case study with them. We received the data from SRP. Those are the actual PMU data from 2 actual oscillation events on November the 3rd, 2023, and also September 20th, 2023. The 3rd event, the data is not available, so we are not able to have a case study for that. Additionally, we got the GPS coordinates for all the substations where the PMU deployed it. And we performed the data pre-processing were performed. So for example, because they forgot to download the voltage angle, this is they did not download them. So we have to estimate the voltage angle by using the frequency measurement as an alternative. And the missing data we replace with the value of the previous data point. And also the channel with no data or constant value, we have to ignore that. And for the specifically for voltage and the frequency channel for September 20, 2023 event, they are in the different data files. So we have mapped the voltage and the frequency measurement by using the name mapping based on their substation name. And also we have to convert the data format into the FOT itself data format to perform the case study. Yeah, this is an answer result for the first event. As you can see, the oscillation frequency is a 0.21 hertz, and roughly each cycle is 5 seconds. The tool is able to identify the hybrid power plant with the PV and energy storage system as location 1 is the source location, and the source type is the active power issue. The tool is able to list the top 3 locations with the highest confidence index as the final result. As you can see, the location 1 is suggested by the tool, and the confidence index is 91.9%. And the result is correct and consistent with the actual event. That means that is to say the analysis results are correct and accurate. That's for the event 1. You can see the oscillation, the frequency measurement is quite noisy. That means they are not, because we observe that there's another local oscillation, forced oscillation 1.8 hertz, and we identify the 1.8 location, and that is correct as well. For the second event on the November the 3rd, 2023, again, the oscillation frequency is 0.25 hertz. And again, this is the estimated the source location is in another hybrid power plant with PV and plus energy storage system, and the source type is active power. Yeah, the results are accurate and correct, which is consistent with actual event. Again, you can see here the red curve here for the frequency measurement is quite noisy. Again, this is a forced oscillation with a 1.8 hertz as well. And the tool is able to identify the source location for the 1.8 oscillation mode as well. Yeah, that's for the case study for the SRP. Additionally, we performed the case study for the EI association event on the January 11, 2019. I think you are all familiar with the event. So it's the troublemaker is a synchronous generator in Florida area, and the valve is repeatedly open and reclose every 4 seconds. So that creates a 0.25 hertz oscillations, and the oscillation can be observed across the entire EI. And the duration is more than 18 minutes. So based on the measurement we connected from the FNet grid eye system, and the tool is able to identify all the 3 methods is able to identify the generator, the location in the Tampa Bay area, in Florida area, it's the source location. And also the tool is able to suggest the source type is a governor, is active power issue. And all the results here is consistent with the actual event. Yeah, in addition to the traditional forced event, here we expanded the tool to the high frequency part. As you can see here, this is the actual event case study for the Dominion. And the troublemaker is the data center connected to the substation F. But the substation F has no PMU deployed. We have the substation, adjacent substation A, B, C, D, E have PMUs. And with the PMU measurement within the substation nearby, five substation nearby, the tool is able to indicate either substation B or substation D as the source location. And the frequency oscillation magnitude from the voltage magnitude is roughly 0.01 per unit peak to peak. The damping ratio, the frequency is 11 hertz. The damping ratio is roughly 5%. So the oscillation can be mitigated by itself. However, the oscillation can be reinitiated every 1 second. The reason is unknown. We guess this is just our guess. It might be the periodical load, but we are not 100% sure. Yeah, as I said, we select the 3 time windows. The oscillation lasted for more than 10 minutes. And we select a few data windows with the highest, relatively higher magnitude in terms of oscillation. And the tool is able to identify the top 3 locations with the highest confidence index. So as you can see, the tool can identify either substation D or substation B as a source location. So if there is a PMU deployed at the substation F, I believe the PMU can identify the substation F as a source location. But in reality, there are no PMU deployed at the substation F, so the adjacent substation B and D are identified as a source location. So somehow the tool can provide some useful information to the system operator to help them to mitigate the oscillations. Yeah, maybe we can, because we have some time, we can talk about the ultra low frequency oscillation as well. So this is a simulation study. Usually the ultra low frequency oscillation is introduced by the time delay of the control loop. So this is one example. This somehow replicates the actual event. This is in PSAC simulation. I intentionally add a buffer and create the delay from the 0.1 second, 0.5 second, and 0.1 and 1 second as a time delay. The control cycle for voltage control at the plant control level is 2 seconds. If we introduce a time delay, as you can see, if we introduce a time delay as 1 second, you can see the oscillation can be triggered. The oscillation frequency is 0.055 Hz. It's pretty low. The reason is that because of delay, the plant controller always sees the outdated or delayed the measurements of active power. So that triggers the oscillations. If we reduce the delay to 0.5 second, and the oscillation can be, it's not a growing oscillation, but we still can see the oscillation. And if we reduce the delay to the 0.1 second, the delay can be quickly damped. So there's no growing oscillation anymore. Based on the simulation data, we input the synthetic PMU data. The simulation result is based on the synthetic 2000 bus Texas grid model, and we input the synthetic PMU data based on the simulation result to the tool. The tool is able to identify the dominant frequency is 0.05 Hz, and also estimate the source location, and also the reactive power exciter is the issue. So yeah, reactive power is the control loop is the issue. So that's to say the tool is able to handle the ultra low frequency as well. So yeah, I think that's pretty much I have. Just a quick summary. We developed a tool to help the system operator to mitigate the forced oscillation or ultra low frequency or the sustained subsequent oscillation to identify the source location or source origin. In addition to the source location, the tool is also able to identify the source type, either active power control loop or active power control loop. And we can tell whether the source is inside or outside your footprint. And the tool does not rely on the system topology, but we need the GPS coordinate of all the PMUs, so we can build the virtual topology to perform the estimations. And we have performed quite a bit case study for simulated results and also the actual PMU result for utility and EPRI members. For the next step, the tool here, we use the synchrophasor measurement as an input, either the synthetic or historical data, or we can use a streaming measurement as input. So for the next step, what we are working right now, we plan to use the synchronized waveform data as input to detect and analyze the high frequency oscillation, because we do see some limitations of the synchrophasor measurement. And additionally, we are working with the utilities and also EPRI members for potential field deployment of FLT tools, online tools. So yeah, that's something we plan to do in future. I guess that's pretty much I have today. I'm happy to answer your question and also your comments and suggestions. Yeah, roughly half an hour. Yeah.